All right, so we got one person who needs a note packet. Anyone else need one? Okay, so welcome back. Proof, set theory, and logic. A Monday. Hopefully everyone had a wonderful weekend. Last time, if you recall, there was an induction proof we started doing, and then we went like, wait a second, let's do this next time, just to be careful. Immediately after class, we realized how to do it, and we were like, okay, good. Okay, so let's go through that one again quick so you don't have a little blank spot in your notes. We were proving this. We wanted to use, and now as soon as we did it, I was like, okay, this is why I picked this example, since it's a good example, but I forgot that was the reason initially. I'll show you. It's a great way, or it's a great illustration of something that occasionally occurs. So we're going to prove that for all positive integers n, 2 to the n plus 1 is greater than n squared. Okay, so as our proof went, we said we proceed by induction. Now, I'm going to start by writing it out as we did before, and then we have to modify. Okay, so for the base case, let n equal 1. Then 2 squared is 4, which is 2 to the 1 plus 1. And would you certainly agree that 4 is greater than, well, 1 squared, which is just 1? Mm-hmm. Right? Okay. So the result holds for n equals 1. Now, assume the result is true for k with k greater than or equal to 1. And I'll say, i.e., assume 2 to the k plus 1 is greater than k squared. We show this implies the result for k plus 1 as well, i.e., that 2 to the k plus 1 is greater than k plus 1 squared. Now, when we did this before, we proceeded in, I would say, like the obvious way. We started with one side and we wanted to manipulate it to get the other side. Yeah? We said, oh, okay. So we said, okay, so to do so, observe that 2 to the k plus 1 is certainly equal to 2 times 2 to the k plus 1. Would you agree with that? Yeah? Mm-hmm. And we said, hey, look, 2 to the k plus 1, by our assumption, is bigger than k squared. So this was greater than 2k squared, right? Okay, now here's the trick, and this will show what we actually have to do. The tiny modification that must occur over here. We will go, hey, check this out. Would you agree that 2k squared is equal to k squared plus k squared? I imagine you'd believe that. And would you agree that you could write k squared as k times k? Would you agree that you could write this as k squared plus k minus 1 times k plus k? You agree with that, maybe? That is, you could write this k times k. If you wanted to even do something slightly easier, perhaps, to see, so maybe less easier symbolically, you could write this as k plus plus k, where this occurs k times, yeah? K times k is just k plus k plus k plus k, k times, right? 3k is just k plus k plus k, right? Same business. Just add k times to get k squared. Okay, so you can group all of these together except for one, right? Okay, so check this out and think about this. Would you agree that this is certainly greater than or equal to k squared squared plus k minus 1 times k plus 1. Well, after all, certainly k is greater than or equal to 1, so yeah, sure. And now we're almost there, but notice, if we want to turn this into the thing we actually want, which is k plus 1 squared, this would have to be equal to a 2. Yeah? Oh, now I see what we have to do, right? We should use our base case as k equals 3. If we do k equals 3 as the base case, and we also show 1 and 2, then from k equals 3 on, this technique will work, right? Does that make some sense? That is, if we go back and we say, if we started here and we said, let k equals, or let n equal 3, then, modifying this very slightly, we just get the following. We say, hey, look, 2 to the 3 plus 1, this is 2 to the 4. That's what, 16? 16. Would you agree that this is greater than or equal to 3 squared, which is just 9? Yeah? 16 is bigger than 9? Okay, so now if I go k greater than or equal to 3, then I could certainly replace this right here with k squared plus 2k plus 1, which is indeed equal to k plus 1 squared, right? So induction delivers the result for n greater than or equal to 3. To finish, we show the cases of n equals 1 and n equals 2 separately. So, for the n equals 1 case, here's what we get. We get, well, it's exactly like before. We get 2 to the 1 plus 1, that's 4, and that's certainly bigger than 1 squared, which is just 1. For n equals 2, we get, well, 2 to the 2 plus 1, which is 8. Would you agree that that's certainly bigger than 2 squared, which is just 4? Okay. Therefore, 2 to the n plus 1 is greater than n squared for all positive integers n. So, my point here is to show you that induction can be part of a proof involving other steps. That is, before we did proof by cases, right? We said, hey, you could have a proof where you have to split it into a couple cases. You can handle each case separately, but doing it all together might be kind of tricky. Yeah? Here, we're doing exactly that. We're doing the case where n is equal to 1, the case where n is equal to 2, and then the case where n is bigger than that. Induction handles the case where n is 3 or larger. If we start at 3, induction takes us all the way there. But for the cases of 1 and 2, we got to do something else. Does that make some sense? Okay, cool. So I guess that's where we went off the rails last time. We don't use it for the whole thing. The point of that problem, the reason I must have put it in there originally, was to show that you can use induction in part of a different proof. That is, you don't have to do induction proofs are just wholly induction and nothing else. They are a valid proof technique that you can use in combination with other valid proof techniques. Reasonable? Sweet. Okay. Questions? No? Great. So, off we go. On to the next little chunk, switchboards. All right. So if you recall, we were just getting started talking about set theory. All right. so recall, sets are collections of objects. If an object X is in a set A, we write X in A, that little E looking thing is the in symbol, the inclusion symbol. X is an element of A. To denote this and read it as X is an element of A, or more casually perhaps, X is in A. All right. If two sets have the same elements, we say they are equal. Okay, so sets are just collections of things. There's no order to them at all. It's not like there's a first thing and a second thing or something like that. There's just stuff, right? Oh, I'm saying it from my writing. There's just stuff in a set. So if sets are just collections of stuff, any two collections that have the same stuff in them are the same thing. That's what we're going to say. Reasonable? Okay, cool. Now, we can extend this notion in the obvious way. If X is not an element of A, we write X with the in sign A, but then we cross it out. It's kind of like writing not equal, right? Equals with a little line through it. Same business right here. So that's X is not in A. Now, a final little piece of notation. Sometimes we will define sets using what is called set builder notation. Which specifies a set via a predicate. Let's call it P of X. For instance, the set A, I'll call it, which is just the x's, and I'll even write it this way. I'll say, I'll start like this. I'll say X in R such that X is greater than or equal to 0 consists of all non-negative real numbers. Now, there's two different ways we can write this. Here's like the components of set builder notation. By the way, quick pause. Has everyone seen set builder notation before? Okay, no, some people haven't. All right. Here's the breakdown of it. So you define a set by putting some curly brackets. Sometimes you can just write out all the elements in the set. But if you can't, for instance, if you're talking about all the real numbers that aren't negative, yeah? You couldn't write them all out. There's a lot of them, yeah? So what you'll do is you'll specify where the thing can live. So some x's belonging to a given universe. And then you either put a bar or a colon, either way, and then you put your predicate. So, set builder notation, here's kind of like the pieces of it. The set of values in the universe U. So this says values in the universe U. This part is telling you that piece. This part is telling you where the possibilities could be, such that that's this little bar. That's starting to look confusing. The predicate P of x is true. And this is the P of x, the predicate. So if we break it down, maybe it's a bit better if I color coded it, but I don't want to redo that right now. But if we break it down, here's the idea. Maybe you haven't seen this symbol, this R right here. But basically it says here's all the x's in the real numbers. So that's just all the regular old numbers, no counting numbers, all the decimals, all the squares, the twos, weird stuff like that, fractions, whatever you want. Just no imaginary numbers or anything like that. No other stuff, no like a picture of a dog or something like that, just numbers. So the things in the real numbers such that the number is greater than or equal to 0. It's the set formed by taking all of the things in here that satisfy this predicate. Does that seem reasonable? It seems reasonable at first, right? We're going to return to a paradox that we talked about last time very briefly when we mentioned, it's called Russell's paradox. But the idea that you can just form sets from things that satisfy predicates with no additional sort of restriction on it actually causes this little tiny bit of trouble. But the basic idea of it, I think, is relatively clear. That is, when you do, say, like a universal quantification, you say, like, hey, for all whatever, here's the stuff, right? Or you do, like, an existential quantification, you say, there exists stuff that satisfies this or something. You can view this, for instance, as the set of all instantiations that would satisfy some existentially quantified true statement. Or if you want to put it another way, maybe the statement's false, that is, there's no instantiations of it, in which case you would end up with a set containing nothing. By the way, we have special notation for a set containing nothing. So a tiny little bit of additional stuff for the set with no elements, we write the symbol, looks like an O with a slash through it. So, i.e., the O with a slash through it is just the set with nothing in it, which always looks weird to write, just set brackets on either side, nothing in the middle, so that's why we write the little O with the slash. It's a little bit easier to read. Otherwise, people look at that and they go like, is that it's like a 33, or is that like a Greek C or something? I don't know, right? It's easy to have your set brackets get messy looking. It's much easier to write a 0 with a slash through it. Yeah. Call it the empty set for obvious reasons. It's the set with nothing in it. Okay, cool. Sets, inclusion, element of that business. The empty set. Statements like set builder notation, where you use predicates to construct sets. How are you feeling about all this? Okay, cool. Let's return very quickly to a paradox we discussed before. So, one thing that, and this is not something that I will like quiz you on here. You don't have to even write this down if you want, but it's fun and it's interesting to see. And I think that it does kind of show you a little bit more of what's going on. We need a lot of tools that we'll develop later in the class to talk about what the implications of this are and how you deal with it. But for now, it suffices to just talk about what this paradox is, because it's fun. And I hope you find it as strange as I do. Okay. So when you want to start trying to like build mathematics from the ground up, if you were doing that, if you were saying, I want to know mathematics from the very basics, what's the stuff that I have to start with? After all, if you want to talk about anything, you have to start by saying, like, okay, suppose this is true. Like, here's some basics, right? Some groundwork, yeah. So we'll take some, like, givens, and then from that, we'll derive stuff. Well, what is the least restrictive stuff? What's, like, the basic stuff you have to assume to build mathematics? Like, all of it. Hard question, actually. It seems like it should be easy. And to all of you who I saw going, like, maybe this. Hey, good. I like that you found, like, believe that's a tractable problem, right? Because other people have too, and they got interesting answers. So here's a little aside, I guess. So Russell, let me make sure I spell his name right. It's got 2 L's. A little aside on Russell's paradox. So suppose we start with sets and the following axioms. So axioms are the things that you assume to be true. So we start by assuming that, like, there exists a set or something like that. You have sets, and you have, like, some notion of inclusion with, like, these very basic types of things. And you add these, like, little tiny axioms. So here's the 2 of them that you need. Extensionality, which says that for all x and for all y, here's the statement. I'm going to write it, and then you'll go, what? And then I'll read it, and then you'll go, oh, okay, that actually makes sense. So for all z, the statement z, or x in z, if and only, or sorry, backwards, z in x, if and only if z is in y. So this statement implies that x is equal to y. That is, they have the same elements. So this statement says, for all sets x and y, if for all z, having z in x implies that z is in y, and for having z in y implies that z is in x, this statement implies that x is equal to y. So another easy way of saying this is that for all sets x and for all sets y, x and y are equal when they have the same elements. Do you agree with that? Okay. Seems like a reasonable place to start. Yeah? Okay. Then the other one is called unrestricted comprehension. Okay, unrestricted comprehension says the following. There exists y such that for all x, x in y, if and only if phi of x for any predicate phi. That is, there exists some set y such that no matter what x you choose, x is in y if and only if phi of x is true. Another way to say this is that you could define sets using set builder notation. That is, there is a set so that the things in the set are just the things that satisfy the predicate. This seems also reasonable, right? Like if you have a statement, something that is unambiguously true or false when you put a value in there, a predicate, yeah? Then we could use that to define a set by picking only the places where it's true, yeah? Feels like these are 2 reasonable things. Okay. Now, let phi of x be the predicate x not in x. Then, instantiating Well, I'll even before instantiating. Let me actually write what that is so it can be really clear. Then, via unrestricted comprehension, there exists some set y such that for all x, x is in y if and only if x is not in x. Yeah? So, instantiate y, after all, the statement is that this is true, right? By the axiom of unrestricted comprehension, this thing that we're just assuming is true about sets. We're assuming it's true that you can define sets using set builder notation, basically. And we're saying, hey, there is some y. Let's instantiate a y. Okay, now this value y is the set such that x is in y if and only if x is not a member of itself. But this is true for all x's. So it's certainly true for y itself. Then instantiate x, setting it equal to this y. This produces the following. It says y is in y if and only if y is not in y. That's a contradiction, right? Uh-oh. Oh no. Here's the easier way to think about Russell's paradox. Basically, should these things be true, then there is a set y such that it is a member of itself if and only if it is not a member of itself. This is the whole y, like define the set of all sets that do not belong to themselves, right? So here's kind of the easier way of seeing it. So you set y to be the set of sets such that the set is not a member of itself. Yeah? So sets that contain themselves, which is not the craziest thing, right? Okay, maybe you can wrap them around like that. After all, it's a perfectly valid predicate, right? You can tell whether a set contains itself or not. Okay. So is y in this set? Then y not in y implies that y is in y, and y is in y implies y is not in y. Right? Since if it doesn't belong to itself, well, this is a set of all sets that don't belong to itself, so it should be in there, right? But if it's in there, well, it shouldn't be, because it's the set of all things that don't belong to themselves. Uh-oh. Big trouble, right? So we get bad stuff as soon as we have these things here. No good, right? That is just these basic, uncontroversial seeming starting points. You don't got what you want. You get something kind of bad. That is, unrestricted comprehension is too bold an axiom. It assumes too much. Perhaps we need something more restrictive, a restricted comprehension perhaps, right? Okay, we won't talk about what that is now, but the whole point of it is that while these things we're doing at the moment seem uncontroversial, right, using set builder notation to define a set, actually there are nuances. There are relatively deep nuances. Very, very luckily for us, though, none of this will matter at the moment. So while all of this is cool and a little bit wild, you don't have to worry about it for the sets that we're going to talk about at the very beginning. It just is a good thing to talk about, since after all, I'm going to introduce set theory to you as it was originally naively introduced to the world, right? With the same kind of initial, hey, this doesn't seem crazy. We could build sets using predicates. Yeah, sure, why not? Yeah, whatever. We can make a set with the stuff that satisfies a predicate. OK, yeah. But is it actually the case? Perhaps not. Perhaps you need a little bit more care, especially if you want to have tricky stuff go on, like sets that are members of themselves, any sort of the self-referential sort of thing, which is useful to have. OK, so Russell's paradox, a nice aside, but a useful one to talk about, since I don't want to ultimately lead you astray or make you believe that these are, in fact, totally uncontroversial things to start by accepting. These are things that we actually should probably be a little bit careful with, these basic building blocks. OK, so let's get used to sets really quick. Let's talk about them a little bit more. We did some examples last time. So here's an easy kind of example that people run into problems with kind of a lot. Let's let, oh, I have not erased enough up here. I've still got a little bit of whiteboard cleaner hanging out. OK. Let X be the set, OK, there we go, set of objects 1, 2, and the set of 2. OK. Notice this set contains elements which are also sets. This is pretty reasonable, actually. In fact, this is maybe what you want. In fact, if you're trying to build mathematics from the ground up with the least amount of stuff possible, maybe you want some way to encode numbers as sets. Maybe it'd be great if there was, you didn't have to assume anything other than the existence of sets. Maybe you could just say something like, oh, we'll assume that there is a set, and then we'll give basic operations for how to make sets with sets and stuff like that, right? Something where we could say like, OK, well, I've got a set, the empty set, and then I could take a set containing the empty set, and that's a new set, and build things like this. Maybe we'll get to that point pretty soon. Who knows? But it's perfectly reasonable to have elements that are sets. It's also reasonable to have elements that are not sets if you want, but then you have to assume that other things besides sets exist, which perhaps is reasonable. I don't know. Depends what you want to do. But either way, notice this set contains an element which is a set. Yeah? Notice that if Y is the set just with 1 and 2, then X is in fact not equal to Y, since 2 is not an element of Y, but is an element of X. That is, the set containing 2 is an element of X, but it is not an element of Y, i.e. 2 is not the same as the set containing 2. Yeah? It is true that 2 is in that set, but they're not the same, right? That is, what I'm trying to, I guess, stress here is that a lot of the times in math before now, you can kind of stack parentheses and like brackets kind of however you want, right? In fact, oftentimes in algebra classes and stuff, if a teacher is trying to write like, 2x plus 1 times 4x plus 6 plus 9, then instead of doing yet more parentheses, like, like minus 3y or something like that, they might do something like, for instance, go like, well, I want to make it really clear what's going on, so I'll do like square brackets. You've probably seen teachers do this. And then maybe if they have like, like times 9L minus T or something like that. Sometimes perhaps they'll do something fancy, like they'll go like, oh, okay, well, I don't want it to be too confusing with all these different parentheses. Maybe I'll turn this into like some sort of like curly brackets or whatever, right? And then like, do that sort of stuff. Here, curly brackets have a very specific meaning to us. Curly brackets denote a set. The things inside of them are its elements, or if we are using set builder notation, a quantified, a statement that quantifies the elements of the set via a predicate and the potential things you could plug into the predicate. Does that make sense? So it's clear, like either it tells you exactly what's in the set just by listing its elements, or it contains a statement about the universe and the predicate used to construct the set. Inside of a set bracket is always the set itself, either described exactly or described via this construction where you comprehend across the universe to get the elements. So it's not the case that you could write like 2x plus 4 and put some parentheses around it. And if I put even more parentheses around it, no one would be worried if I wrote that this is equal to 2x plus 4, right? We use parentheses just like a nice kind of visual thing, right? They denote stuff like multiplication and grouping things up, but you can throw as many more extra ones in there as you want without hurting anything, right? Okay, not the same with set brackets. It's not the case that if you put more and more and more set brackets around things, you just get the same thing. That is, 2 is not equal to the set of 2, and that's certainly not equal to the set of 2, nor is that equal to the set of the set containing the set with 2 in it. You can just keep stacking them, and you keep getting new things. This is 2. This is the set that contains 2. This is the set that contains only, as its single element, the set containing 2. This is the set containing one element. That element is the set which contains one element, which is the set containing 2. Yeah? So one thing to be careful of. It is easy to get these things confused, and it is one of the more common mistakes people run into is confusing elements with each other. Okay, so fun. Now, last time we had written a quick definition, mostly to talk about the in symbol and where it perhaps comes from, some notational stuff. But if you recall, we had a quick little definition. So we said, given two sets, A and B, I'll just write this all across. We say A is a subset of B if every element of A is also an element of B. We denote this in symbols as A is a subset of B. I'll write it this way. Or sometimes people will just write A with the thing without the little bar. Now, occasionally, you may also see the symbol here, which looks extra confusing, but all this means is that A is a subset of B, but is not equal to B. It's like a proper subset. That is, B's got some stuff that's not in A. So if you ever see that one, that's what that means. It's just an extension of the equality notation. Same business with this. You could just use this symbol if you want. People throw this one here to kind of be like, to be clear, it could be, in fact, equal, right? Looks like an equal sign. But whichever one you prefer, I'm fine with you using as long as you are clear and consistent with how you use it. Cool? All right. So formally, how would you write this? What does this mean? What's the statement here? Write this formally. So something like, for all x in A implies x is in B. Yeah? That's what it means to be a subset. If this statement is true, then it's a subset. So yet again, we're not really introducing something new as like a new concept. This is just a compact way of writing a statement that would otherwise be not so short to write. Yeah? We're going to keep doing that from now on. We're just going to keep introducing, like most of mathematics, notation to wrap complicated concepts into symbolically easy to manipulate statements. And on some level, getting familiar with math, I don't want to say getting good at math. You never get good at it. You just get used to it, right? I think von Neumann said that. But on some level, this is most of what it is just kind of trusting that you can keep stacking complexity on top of complexity. And as long as you're careful about things, it all works out. OK, fine. So formally, that's what it says. Not important to focus on that there. But subsets, all right. So subsets, nice. Let's do some examples. The positive integers, also called the natural numbers, and denoted by a blackboard n. Actually, do they write? Yeah. I always forget if the n, yeah, that's right. I always forget if it's like n like that or if it's n like this, right? But it's this one. Also denoted by n like that, okay, is a subset of the integers which are commonly denoted by z. For the German Zahlen, meaning number. Yeah, history, right? OK, so n is a subset of z. Likewise, the integers are a subset of the numbers that can be written as ratios of integers, also called the rationals, and denoted by Q for quotient, which are themselves a subset of the real numbers, commonly denoted by R, that is, the naturals are a subset of the integers, which are themselves a subset of the rationals, which are themselves a subset of the reals. And none of these subsets are equalities. None of these subset relationships here are equalities. That is, you'd be totally justified in writing all of these with little slashes through them if you preferred to do that. Reasonable? OK, cool. Can anyone think of like yet another larger set still if we wanted to make this paragraph extremely lengthy?
Complex numbers.
The complex numbers, why not? Yeah. Can anyone guess what we're going to denote the complex numbers by? A C with an extra line in it. Fun. That is, these guys are a subset of C. Cool. The complexes. All right. Fun. Subsets. Does it make some sense? Returning over here, is X a subset of Y? Is X a subset of Y? No way. There's an element in X that does not belong to Y. Is Y a subset of X? Yes. Is 2 equal to the set of 2? No. Is 2 a subset of the set of 2? No, because this is not a set. This is just a number, right? Maybe we formalize numbers as sets, but even still, we'd probably not have that be true. But what we're saying here is that this here is just an element. Yeah? Okay, fine. So to be clear, it's included, it is contained inside of that. But it is not, in fact, a subset. So to be clear, I guess, with one more example, just to make it super duper clear. The set of 1 and 3 is in the set containing the set of 1 and 3 and 4. But 1, 3 is not a subset of the set of 1 and 3 and 4. Why? Because neither of the elements in this set belong to that set. This set only has 2 elements. One of them is the set containing 1 and 3. The other one is the number 4, right? This set has 2 elements, 1 and 3. Neither 1 nor 3 is an element of this set over here. Does that make sense?
If you added another thing of brackets, would it be a subset?
Then it most certainly is a subset. Does that make sense? Okay, cool. Right on. Maybe this seems easy. If it does, and you're like, okay, stop hammering the point home, that's fine, great. I'm glad you feel like it's easy. But these parts, like, if it trips you up, it's perfectly reasonable. People get tripped up a lot by this at first. And it is difficult to parse through this sea of notation that when you're first introduced to it. What do you think? Questions on this right now? Feeling moderately okay? Okay, good. Well, let's go over to the next board then. Okay, so here, well, let's actually do one more little example just to make sure we got it all down. Just to double check that we got it all. Oh my goodness. Really have to get these boards just like totally dry to be able to write clearly. Define A to be the set with 1, 2, and 3.
Hey, Bryce.
Yes.
It's 11.
It's 11 and the clock in the back of the room is off. More wrong than last time. So that explains it. Okay, I'll see you next time, guys. Have a good one. Cool, thank you.